thank you first of all to the organization and to Fokko Wieringa to give me the opportunity to present this today to you. I will present the loosening of protein-bound uremic toxins using electromagnetic fields on behalf of the MITRAM consortium, and the partners are listed below. And I would first like to go a bit more into the consortium. It's put together from the company IMEC, who is really good at making electronic chips and miniaturizing those. And from IMEC in the US, Veerle Reumers, and in IMEC NL, Fokko Wieringa are leading that. Then myself, I'm at the University Medical Center in Utrecht under supervision of Karin Gerritsen, who leads a research track into trajectory into artificial kidney systems. Then from University of Utrecht, there's Professor Roos Mazereel from the experimental pharmacology department. And they are really good in bioartificial kidneys and also in measuring the PBUT toxins. And finally, the man who came up with the idea behind using these electromagnetic fields for the PBUT removal is Professor Joachim Jankowski from the University of Aachen. And I think many years ago he came up with this idea. And together with all of us, we hope to expand on that and to make it more efficient and to create a useful device for dialysis. And last but not least, I think it's again Fokko who was the driving force to getting everybody together. And this project won the Kidney X Prize last year, or already the year before, which I will now give a brief overview of what we've done so far. First of all, I will give a short overview of what the PBUTs are and why it's so important to remove them. Small disclaimer, I'm also an engineer, so if I make any small mistakes on the biology, please excuse me for that. I will try to explain the principle behind using these electromagnetic fields for the PBUT removal. And finally, I will present the roadmap or the current status of the project and the roadmap for the future that we envisioned and it was enclosed in the Kidney X proposal. So first of all, I think we heard a lot about healthy kidneys already. And what they normally do is to filter the blood. And in the glomerulus, I think 180 liters a day of liquids and solutes is filtered through that. But because we don't urinate out 180 liters a day, in the proximal tubule, a lot of reabsorption and reuptake of solutes and liquid is taking place. But another important factor is taking place there as well, and that's the secretion of additional toxins from the blood to the proximal tubule. So in the blood, what is basically left behind after filtration are the blood cells and the proteins. And then albumin, one of the most important proteins, has these toxins still bound to it. And those are still then need to be excreted from the blood side into the urine. And the kidney, as we just heard, has these organic anion transporter proteins for that, so that they can dislodge the PBUT from albumin. And then, let's see if I can make the pointer work. The big yellow blob represents the albumin protein, and the green dots are the PBUTs that then are actively transported from blood to urine. And these PBUTs, so in CKD, this doesn't happen anymore. So these PBUTs accumulate and they have really severe adverse effects for patients, mostly relating to cardiovascular diseases. The healthy kidney can do all of that, but of course CKD patients do not have that, and they are most of the time reliable. They need to rely on these passive filters to clean the blood. And for most of the molecules that are small enough to fit through these filter pores, that is no problem. However, there are then the protein-bound toxins, as shown below, which in principle are small enough to fit through the filter, but they are bound to this albumin that we really do not want to excrete from the blood. So something else needs to happen that this passive filter cannot do. So here's another, basically the same thing, kind of differently represented. So this albumin does not fit through the filter pore, so the PBUT is not excreted from the blood. If we were to be able to loosen it up, it suddenly fits through the pore. So the only thing that's still in the way of doing that is to find a method to dislodge this PBUT from the albumin. And then the idea from Professor Jankowski came in to use electromagnetic fields for this. And with that, we hopefully can shake the albumin really hard so that the PBUT gets dislodged. And normally it's bound by electrostatic forces, but by then shaking them around, we hope to dislodge them and be able to filter them out of the bloodstream. And maybe not all of them might get disconnected, some might reattach again, but as long as we can get rid of a significant more portion than nothing, which is, any gain is gain in this case, that will really help the treatment outcome. And then back to the initial setup. What Professor Jankowski did is take this dialyzer module and put 2 electrodes on both sides. And then if you apply a voltage between these 2 electrodes, you have these electromagnetic field lines going through the membrane. And these can really then interact with the albumin and shake it around, or at least that's the mechanism we suspect to loosen these PBUTs. And here you can see some of its results. And then you see that there's, in this case for phenylacetic acid, there's an increase in removal compared to the control loop with no electromagnetic field present. And there's some differences in frequency as well. And that's, for some frequencies it might resonate better with the albumin than for others, like an opera singer trying to break the glass with their voice. For some, they can really get the right frequency and others can't. So we think the resonance in this case plays a role in that as well. And so previously you had these 2 really large electrodes with still some of the magnetic field lines or electromagnetic field lines going around the module. What we hope to improve is to couple in this field into the liquid on both the top and bottom of the dialyzer module. And then they would really focus around the pores so that we get the highest field density and the field strength over the membrane to locally shake loose the PBUTs and then immediately transport them through the membrane to the other side. And so this is already what we have done so far from the medical technology and clinical physics department in the UMC. They've made this really nice setup with multiple electrodes that we can then freely activate or not in this dialyzer module. And we've done some initial testing to get a feeling for how the system behaves. And as you can see on the apparatus with the peaks and troughs, we think that if we see a trough, for example, that's when energy is being dissipated into the system. So we see a response of the albumin, and we're now trying to fine-tune which frequencies we see the optimal response. And what frequency and what power is also necessary then to remove this PBUT, because we do not want to use a very high power or a very high voltage. So we are in the process of optimizing all those things. The whole MyTran project, beside this importance of shaking loose the PBUTs, since we're making a very tiny chip anyway, why not add more functionality? So we're also looking into expanding it into having a bioimpedance sensor, a blood temperature sensor, or a hematocrit value sensor. So besides this added gain, we also want to monitor all the parameters during the session. And the microchip has more than enough capability of including and incorporating all these sensors and technologies. And finally, the roadmap that we are, we're still in the beginning of it. So as I said, we're trying to understand the system, and hopefully soon can go to some experiments where we find the right frequency for the PBUT removal. But once we are past that initial important step, we hope to go to the uremic goat model, which was an animal model developed by the UMC Utrecht, which is well understood and well known. And then afterwards, as I think was in the proposal, we hope to be able to add this system to any conventional dialysis method. So it's not something that we make for one purpose. We hope to share it and give it around to other projects as well, that you can use it as an add-on for just additional clearance or removal of PBUTs. And I think also there's a next round of Kidney X coming up. So hopefully we are in time to get some more funding and then make this available for everybody if it works. And finally, the dream is, as we heard before, to get rid of dialysis, but go to something implantable, and in the future, maybe not the near, but hopefully near enough, we hope to add this to implantable artificial kidneys as well. And then finally, a big thank you again for everybody in the consortium, maybe to focus also on the medical technology and the clinical physics people, Bert and Leonard, who've done a lot of work on the setup so far. and of course, Professor Jankowski for coming up with this idea, who is also in the room with us today. So very, very nice that you could be here. And yeah, with that, I would like to thank you all for your attention as well. And if there's any questions, feel free to ask them during the Q&A session or during a break or dinner or whenever you see me in the hallways. Thank you.